What do we mean by a statistically significant intercept term? Well, suppose we have the following population regression line. We can see here that the intercept term is non-zero. Therefore, the intercept term is said to be statistically significant, as its population value is different from zero. Now, suppose instead the population regression line looks like this. The intercept term in this case is equal to zero, so it's said to be not statistically significant, or statistically insignificant. In practice, we can't observe the population regression line, so we use the output from our sample regression line to judge whether the population betas are likely to be zero or not. That is, whether they're statistically significant or not. Alright, so looking at the sample regression output, we simply have to look at the p-value, as Excel has already conducted the test for statistical significance. As you can see, it's larger than 5%. So we do not reject the null hypothesis, and we conclude that the intercept term is statistically insignificant. That is, the population regression is likely to have an intercept term equal to zero. Now, time for a pop quiz. How could we conclude that the intercept term is statistically insignificant, that is, its true population value is equal to zero, when the estimated sample intercept term is equal to 3.33, as can be seen here? 3.33 is clearly not zero, right? Well, this is because the 3.33 estimate occurred simply due to sampling variation or sampling error. Based on the standard error, the calculations indicate that 3.33 is practically equal to zero, and is not sufficient evidence for us to reject the null hypothesis, that is, to conclude that the population intercept is non-zero. Part E. A study reported that every additional year in education results in a $2 or more increase in one's hourly wage. Test this claim at the 5% significance level. Now, for this question, we're asked to test whether beta 1 is equal to a specific value, $2 or more. As Excel and all other statistical software packages only test whether the betas are equal to 0 or not, we cannot simply look to the p-value for the answer in this case. We will have to go old school and answer this hypothesis testing question by hand. That is, state the null and alternate hypotheses, write down everything we know from the question, yada yada yada. This should look very familiar from our hypothesis testing lectures. If not, please be sure to review them. Now, with all regression-based hypothesis testing, we use the student t-distribution as we are given the standard errors from the computer output, which have been calculated from the sample. That is, we're using sample standard deviations. First things first, we have to set out the null and alternate hypotheses. The question asks whether one additional year of education results in a $2 or more increase in hourly wage. So it's asking us whether beta 1 is equal or larger than 2. Now, what is a counterclaim, the exact opposite of this claim? Well, it must be that beta 1 is less than 2. Recall that the claim with the equal sign is a null hypothesis. So we can now write down the null hypothesis and the alternate hypothesis. That's the first step done. Time to write down all the information provided to us. Remember that the null hypothesis is assumed true until proven otherwise. Looking at the null hypothesis, we assume the population beta 1 is equal to 2 until proven otherwise. If we look at the Excel output, you'll see that the estimated sample beta 1 is equal to 1.4719. So beta 1 hat is equal to 1.4719. The standard error is also given to us in the sample regression output. So we write this down. Okay, what type of hypothesis test is this? Recall from the hypothesis testing lecture, we can tell by looking at the sign of the alternate hypothesis. Since it's a less than sign, it must be a lower tailed test. This means the rejection region will be on the lower side of the distribution. Next step is to draw the student t-distribution. It looks pretty much just like a normal distribution. Recall that it's bell-shaped and symmetrical around 0. Since we've figured out that it's a lower tailed test, then the rejection region must lie here, in the lower or negative side of the distribution. And we're told to test at the 5% significance level, which means that the size of the rejection region comprises 5% of the distribution. So the next big step is figuring out the critical value, which is a cutoff of the rejection region. When using the student t-table to find the critical value, we will have to know the degrees of freedom of the sample regression. It's simply equal to n minus k minus 1. N is the sample size, and k is the number of regressors, or x variables. So looking at the output, we can see that the sample size is equal to 40. The number of x variables is 1, as we're only analysing the effect of education on wages, nothing else. So the degrees of freedom is 40 minus 1 minus 1, which is 38. This is a measure of how much information is contained in our sample. Let's look at our student T table. We need to look for the row that corresponds to a degrees of freedom of 38. Scrolling down the table, we see this. Notice that there is no 38 exactly, so we simply round to the closest value and use a degrees of freedom of 40. So this is a row we're working with. Now recall the alternate hypothesis. Since there is a less than or a larger than sign, this must be a one-tailed test. So we'll be looking at the significance levels on this row. The question asks us to test at the 5% significance level. So we're looking at this column here. So the critical value we need is this, the intersection of our degrees of freedom and the significance level. The critical value is equal to 1.684. However, since this is a lower tail test, with a rejection region on the left side of the distribution, recall that the student T distribution is symmetrical around 0, so the critical value is below 0 and must be a negative number. So our critical value is actually negative 1.684. So back to our student T distribution. We now know the critical value, that is, the cutoff of the rejection region. The next step is calculating the test statistic. Back to our Excel output. Now, it's tempting to use the T statistic that's provided by Excel, as it's just staring right at us. Don't. Why? Because this T statistic is testing for statistical significance, which is this test here, whether beta is equal to 0 or not. But in our case, we need to test whether beta is larger than or equal to 2 or less than 2. So we can't just use a computer output in this case. We will have to calculate the T statistic by hand. Remember the formula for calculating the test statistic from our hypothesis testing lecture. This was used for testing the population mean, so x hat is the sample mean, mu is a hypothesized population mean, and the standard error is in the denominator. In the regression analysis, the formula looks pretty much the same, except we're dealing with betas rather than averages. Beta hat 1 is a sample estimate, produced by the sample regression line. Beta 1 is a hypothesized population beta, and the standard error of beta hat 1 is in the denominator. Okay, we're good to go. Subbing in values into the formula, we know that beta hat 1 is equal to 1.47. The null hypothesis, which is assumed true until proven otherwise, states that the population beta 1 is equal to 2, and the standard error from the Excel output is equal to 0.3. Therefore, the T statistic is equal to negative 1.77. So back to our T distribution. We've calculated our T stat, and as you can see, it's smaller than the critical value, so it lies in the rejection region. This means we reject the null hypothesis. So we reject the null hypothesis at the 5% significance level, and we conclude that an additional year of education is expected to result in an increase in wages that is less than $2 an hour. Okay, we're done with that question. To solidify our understanding of regressions, let's go through one more worked example. You sample 25 first-year statistics students and ask them about their final exam grade and the number of hours of sleep they had the night before the exam. You estimate the following regression. Now that we're familiar with the regression output, we should breeze through these next few questions. Write down the estimated sample regression line. Test whether sleep has a positive impact on exam grades at the 1% level. What percentage of variation in grades does variation in sleep explain? Is the intercept term statistically significant at the 10% level? Interpret its meaning. And Sam slept 3 hours before a statistic exam. Estimate his exam grade. There's some new stuff here, but don't worry, it's very straightforward. Okay, question 1. Write down the estimated regression line. Looking at the relevant section of the output table, and recall that the y variable is grades in the final exam and x is a number of hours of sleep. So we can write the regression equation with grades, the y variable, on the left-hand side. We can see from the table that the intercept term is 36.79, and the coefficient for sleep is 6.16. So the estimated sample regression is grades is expected to equal 36.79 plus 6.16 times the number of hours of sleep. Question 2. Test whether sleep has a positive impact on exam grades at the 1% level. Alright, let's write down the claims being tested here. If sleep has a positive impact on grades, then beta 1 must be larger than 0. The counterclaim, which is a complete opposite of that, must be that beta 1 is less than or equal to 0. Remember, the claim with the equal sign is always a null hypothesis, so the other claim must be the alternate hypothesis. Now, writing this properly, we get this. And since the sign in the alternate hypothesis is a larger than sign, this is an upper-tailed test. Next step is to write down everything we know about beta 1. First, it is hypothesized that the population beta 1 is equal to 0. We can see this from the null hypothesis. Now, pulling out the table from the Excel output, we can see that the sample estimate of beta 1, which is beta hat 1, is equal to 6.16, and the standard error for beta hat 1 is equal to 1.58. Time to draw the student t distribution. Remember, it's bell-shaped and symmetrical around 0. Since it's an upper-tailed test, the rejection region must sit here. And since we're testing at the 1% significance level, the area of the rejection region must comprise of 1% of the distribution. Again, the big question is, what is the critical value? What is the cutoff for the rejection region? Let's pull up the student t table. First thing we need to do is to figure out the degrees of freedom. If we look at the Excel output, we can see that we have 25 observations in the sample. And since the degrees of freedom is equal to the sample size minus 2, then it's equal to 23. So we have to look up 23 in the student t table, and we find it here. So this means our critical value lies in this row somewhere. Since the alternate hypothesis has a larger than sign, we're dealing with a one-tailed test, and must refer to the significance level in this row. And recall that we had to test at the 1% level, so we look at this column here. This gives us a critical value of 2.5. So looking at the student t distribution, we now know that the critical value is equal to 2.5. Easy, huh? Now we just have to calculate the t-statistic. Using the t-statistic formula, we sub in 6.16 for beta hat 1. Remember, the computer output estimated beta hat 1 for us. The hypothesized value of the population beta 1 is 0, so we sub that in here. And finally, the standard error for beta hat 1, as given by the computer output, is 1.58. This gives us 3.9. So our setup looks like this, and we want to know whether the t-statistic falls into the rejection region or not. As we calculate it to be 3.9, then it lies here, as 3.9 is larger than 2.5. Since our t-statistic clearly lies in the rejection region, we reject the null hypothesis. This means we reject HO at the 1% significance level. It's always good to write a sentence linking our finding back to the context of the question, such as, sleep doesn't have a positive impact on student exam grades at the 1% level. Time to cover a new aspect of regressions that we've yet to discuss. Question 3 asks, what percentage of variation in grades does variation in sleep explain? In other words, how good is sleep at explaining grades? Well, simply look at the Excel output for the sample regression, and we'll find the R-square statistic here. Convert that to a percentage and we get 39.84%. This tells us that variation in sleep explains 39.84% of variation in final exam grades. Alternatively, we can view this as a regression model explaining 39.84% of variation in final exam grades. The R-square can be interpreted as a measure of how good the regression model is. Does it explain a lot about the y variable, or does it explain very little about what's going on in the y variable? If the regression model explains 39.84% of variation in final exam grades, then the natural question is, how come the model can't explain the other 60.16% of variation in final exam grades? Well, 60.16% of variation is explained by other factors that aren't included in the model. See, we have our sample regression model, but there are other factors that explain exam grades. These are contained in the residual term. So the R-square statistic tells us that only 39.84% of variation in grades is explained by sleep. So what's contained in the residual? Well, all other factors that affect someone's exam grades apart from sleep, such as his or her IQ, how many hours of study, how good their tutor was, etc. These factors also explain final exam grades, but weren't included in the model. So does this make our sample regression a bad model? Not necessarily. Being able to explain almost 40% of variation in final exam grades is already very good. I've seen regressions in corporate finance journal papers with R-squares of 3%, so 40% is pretty darn good. In the next lecture, I'll show you guys how we can include additional factors into the regression model. Part 4. Is the intercept term statistically significant at the 10% level? Interpret its meaning. What's the test for statistical significance again? Well, the null hypothesis is that the intercept term in the population regression is equal to 0. This means that beta hat 0 is statistically insignificant. The alternate hypothesis states that the population intercept term is not equal to 0, meaning that beta hat 0 is statistically significant. Looking at the table of the sample regression coefficients, the test of statistical significance occurs here. The p-value here is testing whether the sample regression intercept term is statistically significant or not. Recall the p-value rule. If the p-value is smaller than the significance level, we reject the null hypothesis. If the p-value is larger than the significance level, we don't reject the null hypothesis. Since our p-value 0.00052 is smaller than 10%, we reject the null hypothesis. Easy, huh? We conclude that the intercept term is statistically significant at the 10% level, so the population intercept term is statistically different from 0. This means we can interpret the value of the intercept term as it's not merely a randomly generated number caused by sampling variation. Now, how do we interpret the intercept term? Let's take a look. Here's a regression output, and we can see that the estimated sample value is 36.79, rounding to 2 decimal places. So the estimated regression line looks like this. When does someone's grade equal to 36.79? Well, when he or she has had 0 sleep, right? Because if sleep equals to 0, then this term will equal to 0. So if a student has had no sleep during the night before the final exam, he or she is expected to score a grade of 36.79. In general, if x equals to 0, then y is expected to equal to beta hat 0. Final question, and it's an easy one. Sam slept 3 hours before a statistics exam. Estimate his exam grade, okay? We simply have to write down the estimated regression line and substitute the level of sleep. So in this case, we insert 3 hours here, which gives us 55.3%. Hey, I'm surprised it even passed. So we estimate that Sam's final exam grade will be 55.3%. Done and done. We've covered a lot in today's lecture, so let's go through a brief summary of each concept. First, population regressions and sample regressions. The population regression is a true relationship between x and y, but we cannot observe this. The sample regression is a regression line that we do observe, and it's what we use to make inferences about the true relationship between x and y. Second, we talked about dependent and independent variables. The dependent variable is affected by the independent variable. For example, wages was our dependent variable. The independent variable, such as education in our example, is not affected by the dependent variable, so the causality runs one way. Third, statistical significance. That is the coefficient likely to be non-zero in the population regression? If it's statistically significant in the sample regression, then the answer is yes. If it's statistically insignificant, then the answer is no. The test for statistical significance is conducted by default in all statistical software packages, such as Excel, SPSS, eViews, etc. Fourth, how do we make inferences about the true population regression using only the estimated sample regression line? Hypothesis testing. We follow the same steps as usual. State the null and alternate hypotheses, draw the t-distribution in rejection regions, etc., etc. Make sure you always use the student t-distribution for regressions, as we always only have the sample standard deviation. We never use the z-distribution for regressions. Residuals. These are other factors that affect y beyond x. Formally, it is the difference between the actual value of y and the predicted value of y using the sample regression line. In our wages and education example, residuals would include factors such as IQ, age, gender, etc. We also covered the error term. Again, it's also the other factors that affect y beyond x. However, now it's the difference between the actual value of y and the predicted value of y using the population regression line, not the sample regression line. The residuals are the sample estimates of the error terms. 7. How to make predictions about y. It's very straightforward once we've written down the sample regression equation. Given the value of x, we simply substitute its value into the sample regression line to make a prediction of y. Remember, this is only a prediction and is likely to contain an error. 8. We also talked about the standard error. The standard error measures a variation in the sample coefficient estimates if we were to resample from the population repeatedly. It can also be interpreted as a measure of how reliable the sample coefficient estimates are. And finally, the R-square statistic. This reports a proportion of variation in y that is explained by the model. It's a measure of how good the model is. And congratulations! You've finished the lecture on simple regressions. Good work, and thanks for hanging in there till the end. The next lecture in the series is on multiple regressions. It's pretty easy if you've got a good understanding of today's material. Thank you for watching today's lecture on simple regressions. We hope it's been helpful. Be sure to check out our other lectures in the series. All the best.